The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Basically, what I like to do, first of all, I like to appreciate and thank you for being here. And hopefully, I'm sure you're not going to be disappointed by the other guy's talk. You know, mine may. So hang around for everything. But what I like to do is talk a little bit about what can the owner expect to get from a 100-year service life specification. You know, nowadays, everybody wants a 100-year service life, a 100-year service life, and it reminds me when I used to have a ready-mix concrete company, and we cast the concrete on a slab, and it had a huge crack down the middle, and the architect was really upset, and he came over and he told me, but can you guarantee me that crack? And I said, yeah, I guarantee you that we'll be there for the rest of your life, you know. But anyway, so it's the kind of thing that you can almost say anything you can, and you don't know exactly what you're saying. But before we go much further, I'd like to ask you, you know, if you know how fast the world is changing. That's something that we don't tend to realize nowadays, those things. But let's talk about what does it take to have a service life. Basically, a service life is going to be the result of the work of all parties involved. In other words, everybody has to be aligned and everybody has to do it correctly for you to get the service life that you thought you were going to get. But unless everybody is lined up and everybody is contributing, it is not going to happen. And that's when things start becoming a problem. But if we look at, let's take durability just as a very simple term. Going into durability, you're going to have specifications, right? And you're going to have design. And you're going to have construction. And the question to you is, can the construction give you durability? Can the design give you durability? Can the specifications give you durability? None of them can give you durability by themselves. You know, what is going to happen is that where the three of them cross is where you're going to have durability, and that's a small portion of any one of all the efforts of everybody else. So basically, when you think in durability and think in service life, you have to start thinking that in my 100% world, there's only going to be about a 20% of it that I'm going to share with other people, and that's where durability is going to be. That's where we're going to really work together, and that's where we're really going to accomplish something. My question to you is durability service life? If I have something that is durable, does that mean that I have a long service life?
Not necessarily.
Not necessarily. I mean, that's the best answer always, right? Not necessarily. You know, I mean, it's true. I mean, we focus on durability, we focus on making this durable. That doesn't mean I'm going to have service life. So we have to understand the difference between service life and durability. Let's think of some aspects of durability. Sulfate resistance, alkali-silica reaction, permeability, steel corrosion protection. Where? That's just a few aspects of durability, right? But now let's think about what are a few things that affect these things. Okay? Let's put a few, because they didn't have much room to put them. But you know, on one side we have the cementitious material chemistry, we have the Portland cement, we have the pozzolans, and if you go to different countries, you may have cements where 1157, you know, which means that if it gets hard, it's called cement. Because, you know, some places you have 10% addition, some places you have 30% addition. Some places you have 35% addition. Okay? So the world is getting very complicated. Then you have the mixed proportions. You have the water cementitious material ratio, the cementitious content. You have the aggregates. You have the aggregate characteristics. You have the permeability, which is affected by pozzolans, by water cementitious, by consolidation. And then you have construction, which includes the consolidation, the curing, cracking, finishing, and jointing. So let's look at one of these. Let's look at sulfate resistance. Well, the sulfate resistance is affected by the cementitious chemistry, the proportions, the permeability, and all construction. Huh? And in ACI, we try to come up with one or two numbers, right? Wow, and that'll give me durability. Then let's look at the alkali-silica reaction. We have chemistry of the cement. We have proportions. We have aggregate characteristics. We have construction. Let's look at permeability. It's affected by the chemistry of the cementitious material, by the proportions, by the permeability, by the construction, the curing. And then let's look at that. Let's look at corrosion protection. It's affected by the chemistry, by the proportions, by the permeability, by the construction. So it's a mess. So anybody that thinks that durability is something very simple, it is not. And it's something that really takes the effort of all the parties to make it work. And you have to really get concentrated on how all these materials even start working one with each other. And that even affects it further. So we're talking something that is very complicated. But 100-year service life means what?
Costs a lot.
We'll get into that. Does it mean that the structure has to have a service life of 100 years? Or does it mean that a member, the beams have to have a 100-year service life? Or does it mean that the materials have to have a 100-year service life? Does it mean that the concrete is durable, but I don't take care of the structure for it to give me the service life? I mean, what does it really mean? I mean, it's something extremely complicated. So, for example, the service life means that the structure, the members of the material can still perform 100 years from now what they do today. And I don't think I can blow the candle when I turn 95. You know what I'm saying? What does it mean? What does service life mean? Does it mean that 100 years from today I can still do what I'm doing today? Because that's a very sorry picture, don't you think? If I'm designing something today and I give you 100-year service life to do the same thing, I can think of structures where that may be true, the Panama Canal, big dams and all that. But that's only a handful of structures type that we can expect to do the same thing. What are we talking about when we specify 100-year service life? By the way, I'll guarantee anything over 10 years. I'm not planning on being around, I'll be retired, but they'll have to look for me somewhere else, you know what I mean? But anyway, what are we talking about when we specify 100-year service life? Are we talking 100 years plus or minus what? You know, as the picture says, when you ordered a load of concrete, did your office tell you how much that actually was? But are we talking plus or minus 50 years? Are we talking plus or minus 25? Are we talking plus or minus 10? Because I don't know any of those. Let's just be realistic. I mean, what do we mean by that? So, for example, let me ask you a question here. You have a 50-year service life, and I have a 100-year service life, right? My question to you is, can I turn off the switch after 50 years? So, I mean, I'm going to give you a structure that lasts 50, but doesn't last 75. How do I do that? Is 50 years concrete half as good as 100 years concrete? It should be, right? Because if we say there's a difference between 50-year service life and 100, there must be a difference between those two. So, for example, how much are the cost savings between 50 years concrete and 100 years concrete?
Astronomical.
I won't have the credit, right? We need to understand this. I mean, we need to be realistic about what we're talking. We have to know what construction is. And this is one of my topics, for example, where ACI, which in my opinion is maybe the wealth of concrete knowledge tremendously, but we're missing that application of all of that in the construction for the benefit of the construction industry. You know, we're missing some touching things there. But let's put it this way. I have the specifications, plus the design and plus construction, and then I'm going to add to that use and exposure, and then that gives me service life. Now tell me, do we know what the use and the exposure are for the next 100 years? I was hired one time by people in another country because they were going to do the highway system, and they wanted me to develop the specification for 100-year concrete. And I go there to the highway guy and I said, but can you tell me what the exposure conditions are? They say, any. I mean, what's that, any? People don't like to take responsibility over things. And then add the role of maintenance in ensuring the service life of a structure. 100-year service life doesn't mean that you're not going to give it maintenance. And if you don't give it maintenance, you're stuck. So 100-year service life means that a few bars are not going to corrode here and there. I'm going to do a little bit of patching, or that I'm going to get cracks here and I'm not going to have to seal a few cracks. Is that what 100-year service life means? No. But let's talk 100-year service life. Is that a dream? Is that a speculation? Is that the best effort? Is it a subjective thing? Is it an objective thing? What's a 100-year service life? For those of you that know Spanish, I call it una paja mental. And then I woke up, you know what I mean? So anyway, what is it? What's a 100-year service life of all of those things? And then, can you tell me what proven technology exists today that justifies a requirement to be met by the concrete to guarantee a 100-year service life? Can you tell me what technology we have today that will tell me what I have to put in the concrete specs so that it will guarantee me that it will last 100 years? Proven technology that guarantees me. Not a dream or a speculation or a subjectivity. A proven model that gives me 100-year service life for the uses, for the exposure, for alkali-silica reaction, for sulfur resistance, for corrosion protection, for all that. So let me give you an example that happens in front of all of us. It happens in front of all of us, and we do it every day, and we blow the requirements of durability, and we sign off on it. Let's get an example. Let's talk about performance specs. So performance spec, somebody has to determine what is needed, right? Somebody has to say, well, this structure needs this. And then they have to say, if I need that, then they have to determine what I have to specify based on what I think I need. Then I'm going to have a field quality control program, because when I build it, I have to do some quality control program so that whenever the construction goes, I'm back on what, I'm getting what I need, true or false. I need that, right? That's a basic concept. Let's say that we need strength and durability. And let's talk about typical specs. Let's say that we need strength and durability, so we specify a concrete strength and a water cement ratio, right? That's typical. And then I have a quality control program that what I'm going to do is do strength, cylinder strength, right? I mean, I'm doing slump and air and all that kind of stuff. But let's say that all of those things meet, and I'm going to specify my quality control, I'm going to check strength. Because you're the structural engineer, and they're going to send you the brakes. And when they send you the brakes, what are you going to do? If I'm asking for 5,000 and I get 5,001, it's okay. That's all you're going to do as a structural engineer. And you're the one that determined what was needed, you wrote the specs, and now they're going to send you the results, and you're going to say, yeah, that's what I need. So the thing is good. Let's get an example. I need strength and durability, so I specify 3,000 PSI and water cement ratio of 0.45, because I have all of the ACI committee reports and all that, and I know that I need 0.45 water cement ratio. So I come in. Now what happens is the contractor gets a submittal from the ready-mix company, and then they send me the results, right? So because the specs call for a water cement ratio of 0.45 and the specs need 3,000, what will happen is that the submittal at a water cement ratio of 0.45 is going to break on an average much above 3,000, maybe 5,800. That's the nature of the beast. That's always going to happen. Whenever we go in this 0.45 water cement ratio, 0.4, the strengths are going to be way above what structurally we need, right? I get a submittal, and you're the structural engineer, and they send you the submittal, and you don't know anything from Chinola when they come in, and you don't even know what the admixtures are, but all you know is that somebody said water cement ratio 0.45, and hey, in any school, they taught me, my mother taught me that 5,800 was more than 3,000, so that's okay. But now, let's say that the job is going, and we get some brakes, and I get some 5,500 PSI brakes. And what are you going to do? Okay, no problem, Jose. We're going crazy. I mean, hey, look at that guy. That's giving me PSI because all I needed was 3,000. But then when you get 3,300, what are you going to say? Okay, too. Because anybody, including my mother, knows that 3,300 is more than 3,000. But my question to you is this. Does that concrete have a water cement ratio of 0.45, which is what I needed for durability? No. And we do it every day. And then afterwards we wonder why the concrete is corroding and the rebars are corroding and we're getting all sort of problems in the structure because we, the engineer, that's why you have to sue the engineer. When this happens, we bring the engineer in and you feel sorry for him because he doesn't even know what's going on. But he signed off on everything. So, man, his insurance is there. But he blew it. He's the one that wrote the spec. He's the one that approved the submittal. And he's the one that approved the cylinder brakes. So now when I take a course, send them to David Rossi, he said, man, this has more water than the Niagara Falls, you know? Yeah, but it broke at 3,300, which is more than 3,000. And in all of that, the guy's guaranteeing a 100-year service life. We have to understand what's going on. We have to understand the world we're living in. So service life requires thinking outside of the box. And thinking outside of the box, so we think a job like this. This is a little bridge in Puerto Rico at a rice grain terminal. Hey, the corroded rebars at least are holding the little dinghy there. But after in Puerto Rico, we put everything to use. But I'll tell you one thing. What's the problem there? Yeah, that's right. You could have a lot of problems, right? That's why when you go to a job, the first thing you do is what? Say nothing. You know? I mean, unless you can improve on silence, keep your mouth shut. You know what I'm saying? I mean, that's the number one rule. But you know, somebody would say, oh, the steel is corroding. Let me tell you one thing. The steel is supposed to corrode when the chloride ions get to it. Period. So the steel is doing what it's supposed to do. The question is, why is it that the chloride ions are getting to the steel? Is it the permeability of the concrete? Is it the cover of the concrete? Is it the sulfur resistance of the concrete that is causing degradation of the concrete cover, and therefore now the chlorides get there even though you have the right permeability? You have many, many different things, you know, that could go. So you have to think of all the possible aspects. And then what's a big problem? The big problem is in construction, we have a problem that we use bad concrete to satisfy the specs. Have you ever seen that? You have a specs, and all of these concrete, this one, this one, this one, this one, they all have the same water cement ratio, and they all have the same slump. So they all meet the specs. However, it's not the same thing to date this guy as to date this guy or to date this guy. You know what I'm saying? But they all meet the specs. How can that be? What is the engineer's responsibility in the constructability since they wrote the specs? We're forgetting that. And you know what happened in the industry, and this happens every day. A contractor never has enough time to wait for the concrete to have, let's say, a low permeability. Because somebody comes back and says, I want the specs to have a C1202 resistant to chloride penetration of 1,500 coulombs at 28 days. And they say, but why at 28 days? Well, because the contractor cannot wait 6 months to find out if it meets 1,500 or not. So he says, I have to test it at 28 days. So for you to have concrete that passes that spec at 28 days, what do you have to do? Use bad concrete. You're going to use this guy, because this guy has silica fume and all that kind of stuff, so you're using that guy so it passes the test at 28 days of C1202. But in the meantime, what happened in the bridge? You get a heck of a lot of shrinkage, you get a lot of cracking, you cannot finish that concrete, you get a lot of heat buildup, but hey, that's not in the specs. So I use back concrete. And that was a big problem that was happening in Puerto Rico. Because in Puerto Rico, we had the problem also of not only having a lot of sulfate exposure in marine concrete and all that, but we have a lot of heat. And when you add heat to silica fume concrete at 28-day permeability, you're playing Russian roulette. So what happened was they said, how can we avoid that? And the first question you have to decide is when it's important to determine at what age after placement must the concrete show that it meets the requirements in the specifications to ensure its durability and service life. My question to you is, if you're building a bridge deck, or you're building a pier, do you need that permeability in the first 28 days? No, you need it in a year. I don't care if the chloride penetrates 1/4 of an inch or 1/8 of an inch or something like that, not even that much. But am I going to now have a concrete that cracks and all that so that I can meet at 28 days? So as a result of that, we did a study at the University of Texas when I was teaching, because you know that graduate students is the only form of legalized slavery in this country. You know, graduate students have nothing but a lot of energy, a lot of willingness to do a lot of work. I mean, she was here doing homework when her buddies were drinking beer back there at the opening section. So what do? We come in and we say, hey guys, let's do the following. We're going to bring a ready-mix truck here. And I had a few students, and I said, each one of you is going to come up with any concoction you want between 0 and 28 days of accelerated curing, slow curing, whatever you want, for 28 days, and then we'll test the permeability at 28 days. But in the meantime, we're going to have concrete cylinders that we're going to put in water, and we're going to keep them there for a year. And at the end of the year, we're going to find out who wins. And we did it with many different kinds of mixes, okay? High cement content, low cement content, high stone, and all that. So the big question is, okay, so I need strength, I need permeability. When do I put it in service? So you have to always remember that not everything is correct. Like, you know, even Noah's Ark had a problem. The woodpecker had to go. But anyway, we developed a specification, and this specification is a specification that doesn't have water cement ratio. It doesn't have water cement ratio because, as far as I'm concerned, who cares? What does the water cement ratio tell me? I don't know what the water cement ratio tells me, or water cementitious material ratio. It doesn't tell me anything. It had no slump requirement. I apologize for the Spanish part. Why the heck do I care about the slump? Let the contractor get together with the concrete supplier, and if he's going to pump and he's going to do this, he's going to do that. I want it well consolidated concrete. Let them decide on the slump. And we optimize. We don't have a minimum cementitious concrete. In fact, you can add fly ash 40% by weight of Portland cement and 20% by weight of sand at the same time. And you know why that was? That was because the structural engineer division said, we will not accept more than 20% replacement of the cement with fly ash. And we said, well, but what about if the rest we added replacing sand? I said, oh, that's okay. Hey, whatever it takes, you know what I'm saying? Well, I mean, they already finished school, so we're not teaching them anything, okay? And we emphasize durability, temperature, permeability, durability, reduce cracking and curing. So we have a spec that comes in and says, okay, you're going to have a requirement of 1,500 coulombs, but the way you're going to test it, you're going to test it at 28 days following an accelerated curing program. And this accelerated curing program consists of the following. How can we predict the permeability of mature concrete 6 to 9 months based on a 28-day test? Well, very simple. I had all the students, and then can I do an accelerated test, testing at 28 days that will give me the moist curing. So if I come in and I moist cure the cylinders between 0 and 7 days at 73 degrees Fahrenheit, the regular moist curing procedure and all that, and that's very important because you need to have good hydration on the concrete before you accelerate, okay? And then you put it at 100 degrees Fahrenheit between 7 and 28 days, you're going to match fairly close what is going to happen in about 6 to 9 months. And what we do is we have a system of coolers, and this method is approved by the Federal Highway Administration, using bridges and all that kind of stuff. You put the cylinders there, and then let's look at an example. I can have a mix without fly ash, with a water cement ratio of 0.55, that at 28-day moisture give me 7,000 coulombs. That's not good. But at 6 months, give me 45. And then if I accelerate cure, give me 5,500. For the same water cement ratio, I will have different performances. So the end result is this. If this is a 28-day moist cure performance of a mixed design, obviously I'm not meeting 1,500, right? But that's good concrete. That's concrete I like to use because it's good mud. Now, if I cure it for 6 months, I get these values. And now I have this one with 20% fly ash that gives me 1,500, and this one with 30% gives me less than 1,000. So now the question is, man, I want to use this good concrete, but I want to be able to show in 28 days that I can meet 1,500, this number. So this accelerated cure process will tend to match, it'll be somewhere in between those two. In this case, we will use 30% cement replacement because it met at 6 months my 1,500. But now I don't have to put silica fume. And I have a good concrete mix. One that can be pumped, one that can be finished, one that has lower shrinkage and all that. But I have to decide when is it that I need the durability. Let's take alkali-silica reaction. Alkali-silica reaction needs reactive aggregate, alkalis, and moisture, right? And now I want 100-year service life. Well, let's say I want 50 because I don't want to pay too much. So tell me, you get this concrete, which is, my understanding is from David, that's the airport we landed in. How am I going to say that that thing is going to have 100-year service life, 50, 10? How are you going to do that? Well, you may stay like this forever. You may get to hell next month. And then on top of that, you get a free thought, then it will get compounded and all that. So how will I handle that? Tell me which one of these tests tells me that I can do 100 years and not 50, or that I can do 50 and not 75. In some aspects of durability of concrete, it's either durable or not durable. But I can have a switch with dial from 1 to 10. It's either on or off. Either works or it doesn't work. For example, you get a material which is mostly reactive. 98% of the materials are reactive. So how many years is it going to last? Then you have the ASTM C1260, right? That we do a quick test. And my question to you is, right here is not predictable. Here it says that it's going to react. But does that mean that it's going to last 10 years? Or does that mean it's going to last 100 years? And if it is in kind of a little bit drier environment, will it last 100 years? But if it is wetter, it will be, how do you know that? I don't know. There's no technology, in the ASTM, there's no testing to tell me what to do or what can I do. Or you come here and you send a cord to David Rustin and he come back and tell you, wow, I got a very beautiful crack full of gel. I said, now so what? What does that mean? Does that mean that that concrete is going to not last? Because the performance of the concrete is not necessarily directly related to what I see inside the concrete. It takes more reactions before I can affect the performance of the concrete. So all of this goes involved in durability of concrete. And then we got the latest version of ASR. We call it the warts. We have been getting this for about 10 years in Texas. We get all these warts coming in the concrete. It's pretty nice, very nice. The whole thing started one time when a lady came in on a rainy day. She pulled up into her garage, and when she got out, she slipped and fell down. Because, the gel got very slippery because the car was dripping water and all that. Then we started looking, and we had done about 3 or 4 jobs like this, warts. We got one right now that's pretty nice. What does that mean? There's no cracking. This doesn't cause any cracking in the concrete. No cracking at all. So what do you do? And you know why this happened in one case that we're looking at? The engineer wrote and said, you're going to put a polypropylene covering the whole foundation, right? And then the contractor comes back and says, that engineer is damn stupid. How am I going to get all this plastic and shove it down the beams, the great beams? You know what I mean? To be able to get good support. So he asked the engineer, I said, hey, engineer, why don't I lay it flat and take a pocket knife and cut it down the middle in the great beams and then flap it down, and because that's a thick part of the slab, not going to be any problem with moisture coming through. Well, guess what? You start looking at that and all the great beams is where the warts are happening. Because the water comes in on the sides, and then it gets to the top and you get it there. So whose fault? And when you go there and you send the course to David, David will look at the famous sharp particles and he'll see, look at how pretty, that's the gel and the gel is going out through there and the lady fell down. How do you put years on that? And who's causing that? What's causing this? Some people say that what happened is that whenever you give it a hard crawl finish to the concrete, you increase the alkali contents on the top surface. So those reactive particles are more reactive close to the surface than further down inside. I don't know. We don't know. Nobody knows. And then let's talk about sulfate resistance. We have this nice pier here. Then I'm going to do everything that ASTM ACI says. I'm going to go in and do the moderate sulfate resistance because that's seawater. I'm going to have this water soluble, these parts. I'm going to use this cement, that water cement ratio. That's correct. Where does it say there that this will last 50 years, 100 years, 10 years, 20? It doesn't exist anymore. So the question is, when we say 100-year service life, now let's add another component, cracking. Then let's do it because we design structures assuming what? It's going to crack. Okay? Then, ACI, 318, everybody assumes it's going to crack. Then you have material properties, then you have joints, then you have construction. And then my question is, when you add all of that, are the gloves up now? And it's 100 years or more? So the moment it cracks, what happens? Gloves up. And not only that, ACI says you're going to design it so it cracks. Because you know what? My question to you, can anyone afford to design and specify a concrete structure that will not crack? It's almost like we're playing with the same thing, and we don't even want to recognize what we're saying. So, okay, now what? In conclusion, we started asking the question, what can the owner expect to get from a 100-year service life specification? And my question is, do you get a 100-year service? In my opinion, what you get is the best effort of all parties to achieve the most service life given today's technology, codes, construction practices, predictions, and maintenance, and budget. That's what you do. What you're going to say, I want a 100-year service life, I'm going to throw a book at it. I'm going to do the best I can with the design and the budget and everything, and I'm going to allow a few cracks here, a few cracks there. I'm going to put a maintenance program that we're going to seal cracks and do all that kind of stuff. And then we're going to do the best we can. That's all we can do. So 100-year service life, do we mean 100-year service life, sulfate resistance, alkali-silica reaction, corrosion or reinforcement, where, what? What do we mean? I have never seen a spec that says 100-year service life. I never tell you what damage in 100 years, All these aspects of durability have more or less possibility for control because it's easier more or less to control the properties of the product that go into. But in terms of the overall structure, service life is a different game. So I started by asking you, how fast is the world changing? Don't worry, it's already there.